Welcome back. In the previous video, we introduced the concept of logistic regression, a method used for classifying data into binary or multi-class categories. In this video, we will formalize the notation and further elaborate on the underlying principles of this approach. Let's develop a notation first. Let us say we have m data points, and each data point has n components. For example, we might say in a classification task, we consider 12 features for each data point. So n equals 12. Say we have 10000 samples that we can use to train, and so m equals 10000. The output y is a classification group among, say, k groups. K equals 2 if it is a binary classification. To use vector notation, we say theta is dd dimensional vector, where d is the subset of the most important features from n features we choose to train the model. The linear hypothesis function h theta maps each of n-dimensional data points to one of the categories. Our loss function is based on what is observed and what is predicted. For example, if the observed is 1 and predicted is 0, then error is 1. We can choose from many loss functions. The goal is to minimize the average loss over all observations. Let us see how logistic regression helps in cancer diagnosis. We'll start by understanding the key components. The input features, which are the variables we use to make predictions, are taken as mean, area, and concavity. We do not know if these are the best features to use, but let's go with that for now. The output is a classification, typically whether cancer is present or not. Our task is to determine the model parameters that best fit our data. The hypothesis function is the core of logistic regression. It helps us calculate the probability of the output being in one class. Essentially, this function guides the model in making predictions based on the input features. By tweaking the model parameters, we aim to improve accuracy, making this approach vital in medical diagnostics. Let us define h theta x as the probability that prediction is 1, cancer, given an observation x, and parameters theta. For example, if you make an observation of mean equals sign 0.7 and concavity equals 0.5, and if we have trained parameters of theta as 0.7 minus 0.2 and 0.3, then we can compute h theta x to be 0.7. So we predict that there is a 70% chance that patient has a malignant tumor. One issue coming out of linear regression is that the output h theta x can be outside of 0 and 1, so we need a function to normalize the value. In this case, we will introduce a nonlinear function. So how do we take a linear model and nonlinearize it? Here, we introduce the sigmoid function. It is a powerful tool in the world of logistic regression, transforming any real number into a value between 0 and 1. This characteristic makes it perfect for modeling probabilities. Imagine it as a smooth curve that quickly approaches 0 for negative inputs and 1 for positive ones. Consider an example. If our function's output h theta x equals 5.4, the sigmoid, denoted as g of h theta x, calculates this to approximately 0.99. This result uses the formula g of x equals 1 over 1 plus e to the power minus x, demonstrating how effectively the sigmoid function can predict outcomes close to certainty. So how do we predict the value to be 0 or 1? We say if gh theta x is greater than or equal to 0.5, we predict y equals sign 1. Conversely, if it's less than 0.5, y equals sign 0. So here's another example. Suppose h theta x equals minus 1 plus x1 to x2. This equation uses three parameters, theta 0, theta 1, and theta 2, which are minus 1, 1, and 2, respectively. When we input new values for x1 and x2 and apply sigmoid function, the model calculates a result. If the result is 0 or more, we predict y equals sign 1. If it's less than 0, we predict y equals sign 0. This decision rule helps classify new data points based on their features x1 and x2. Understanding these predictions is crucial for making informed decisions with data. So far, we only looked at linear boundaries, but as shown here, nonlinear boundaries are possible and make more sense in some classification tasks. In the next video, we will look into the actual implementation of these ideas. See you soon.